the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, which is for linear algebra students who are currently going through eigenvalues and eigenvectors and are now learning about diagonalization, we will approach the diagonalization theorem. Now that's a mouthful. It's hard for me to actually say. Before we get to the actual theorem, I want to motivate parts of the theorem with an example. So let's take a look at this simple little 2x2 matrix and compute the eigenvalues and eigenvectors of that matrix. It's just a good review anyway, so let's go ahead and do that. Remember, X is an eigenvector of this matrix if that matrix times that vector X is just a scaled version of that vector X. That scalar is known as the eigenvalue, and we say that X is the eigenvector associated with the eigenvalue lambda. Now we're being asked to find the actual eigenvalues and the eigenvectors for this matrix A. To do so, we'll just subtract lambda X from both sides. We'll factor out X. We'll recall that we have to put the identity matrix on that lambda, otherwise that subtraction in there is completely bunk. So we get to this point right here. We'll remember one other thing, which is that eigenvectors are never zero vectors. And because of that, this homogeneous equation must have non-trivial solutions. That is, this matrix is a singular matrix. That is, it's not invertible. That is, the determinant is equal to 0. So let's go ahead and set the determinant of that matrix equal to 0. And now I'll go ahead and move away from the symbolic version of this and just actually figure out what the determinant of A minus lambda I is. And we get down to this right here, which is known as the characteristic equation. In fact, both this and the equation above are known as the characteristic equation. So simplifying this characteristic equation, we get the following. And cleaning this up, we get to our two eigenvalues. Now, if you've been watching my video series so far, we haven't really worried about finding eigenvectors yet, but now we're going to start doing so. Really, the eigenvectors associated with the eigenvalues are easily found by solving the related homogeneous equation with those lambdas plugged in, this homogeneous equation right here. For example, I happen to know that lambda equals 3 is an eigenvalue. So let me write that down. And for that eigenvalue, I know that A minus lambda I, which I didn't really write down. I wrote down in the determinant form, but let me go ahead and write that down. Let's do it up above over here. There we go. So when lambda is equal to 3, that matrix ends up being a 1, 3, negative 2, and what is that, a negative 6? And we want to find out when is A minus lambda I times X equal to 0. In other words, we want to solve A minus 3I times X equals 0. Now, I totally know that X equals 0 is a solution of this. It will always be a solution of all of these homogeneous equations because the trivial solution is always a solution of a homogeneous equation. However, since eigenvectors cannot be zero vectors, we have to find the non-trivial solutions of this equation. Putting this in an augmented matrix, you can easily see that row 2 is a multiple of row 1. So this augmented matrix is equivalent to that augmented matrix. And when I say equivalent, I mean row equivalent. We have a single pivot and a free variable. X sub 1 is equal to negative 3x sub 2, x sub 2 is free, and so we can describe the set of solutions to this homogeneous equation using this parametric vector equation. And it turns out you could choose any value you want except for 0, so any non-zero value you want for x sub 2, that's what that was supposed to be. And in general, most of us will choose x sub 2 to equal 1 to get our eigenvector that's associated with the eigenvalue of 3. And I'll note that as x sub lambda equals 3. In other words, this is the eigenvector for the eigenvalue 3. Now, as we've said in a previous video, there's actually an infinite number of eigenvectors associated with that eigenvalue. In fact, any scalar multiple, any non-zero scalar multiple of that eigenvector is yet another eigenvector for this specific eigenvalue. So, as your instructor probably should have told you, answers will vary slightly here. We have found the eigenvector associated with lambda equals 3. Let's go ahead and do this all over again with the eigenvalue lambda equals -2. We'll take a minus lambda I multiplied by x and set it equal to 0. That is, we're just going to set up an augmented matrix with a minus lambda I on the left-hand side of the augmentation bar. And again, you should be able to note here that row 2 is just a scalar multiple of row 1. This augmented matrix is row equivalent to 2, 1, 0, 0, 0, 0. That is, we know that twice x sub 1 is equal to negative x sub 2, and x sub 2 is free. And you could write that as x sub 1 is negative 1/2 x sub 2. The general solution to the homogeneous equation is this guy right here. Now, I did tell you in the previous part that we generally just say, oh, let that parameter be 1. However, there are exceptions, and this is one of those exceptions. I dislike having fractions, so I'm just going to let x sub 2 equal 2. If you allow x sub 2 to equal 2, you get one of your eigenvectors, and remember, there's just an infinite number of them. If you do that, you get this guy for your eigenvector that's associated with the eigenvalue -2. So we have successfully found both eigenvalues and their associated eigenvectors. But there was more to this problem than that. We're asked to compare this to the result in the previous example, and because you've just opened up this video likely, you don't know what I mean by the previous example. Well, in the previous video, we did an example, and it looked like the following. So here's the example, and notice that matrix A is the same exact matrix we're dealing with in our current example, and we were asked to diagonalize A. Well, there's a couple things I want you to notice here. The matrix that we used for the similarity transformation to get our diagonal matrix D consists of column vectors that are -3, 1, and -1, 2. If that doesn't look familiar to you, let me hop back. We're back to our example here, and notice our vectors are -3, 1, our eigenvectors are -3, 1, and -1, 2. Now, I told you in the previous video, we haven't even discussed how we're going to find those matrices for the similarity transformations, but now you kind of see how we're going to do that, at least in a very special case. It looks as though that matrix P, which is invertible and which creates the similarity transformation to create our diagonalized matrix that's similar to A, has as its columns the eigenvectors of A. But that's not the only part. Note our eigenvalues are 3 and -2. And when we go back to our previous example, the diagonalized matrix has 3 and -2 as its only entries. 3 was the eigenvalue associated with the eigenvector -3, 1, and -2 was the eigenvalue associated with the eigenvector -1, 2. By the way, the order of that matters. Notice the yellow vector in the matrix P is associated with the eigenvalue in column 1 in the diagonalized matrix, and the blue vector in the matrix P, which is the second column of matrix P, is associated with the eigenvalue that's shown in the second column of D right here. This is a very powerful result. So let's go ahead and start justifying that result right now. Suppose we're given a square matrix A, and we happen to know that matrix A is diagonalizable. Well, remember what that means for us. When somebody says we have a matrix that's diagonalizable, it just means that we have some type of similarity transformation that can transform that matrix A into a diagonal matrix. And that's what I'm saying here. Then there exists an invertible n by n matrix P such that P inverse AP is equal to a diagonal matrix. Now it's going to help out quite a bit if we introduce some notation for both the matrix P and the matrix D. Now that we know A is diagonalizable by assumption, we're going to go ahead and just say, well, because we know a matrix P exists, we're going to write a version of it right here. We're going to let P just be a matrix of column vectors that we're going to call P sub 1 all the way to P sub n. Now the matrix D, we don't actually need to write it as column vectors. We just know the vast majority of the entries in the matrix D are going to be 0. It's a diagonal matrix. All we need to do is come to the table with some type of notation for its diagonal elements. And that's what we get right here. We're going to let D equal the matrix that you see right here. Now what I'm trying to show here is that if we have a diagonalizable matrix, then the columns of P, these guys right here, should be the eigenvectors, and the entries along the main diagonal of D should be the corresponding eigenvalues. Well, let's see, how are we going to get there just from this statement alone? Well, we're going to go ahead and use this little bit right here. Since P inverse AP is equal to D, I can go ahead and multiply both sides by P inverse on the left to get the following. And usually people don't quite understand why I would do that. However, it just allows us to talk about, without talking about inverses, it allows us to talk about matrix multiplications. I don't want to have to find the actual inverse of P here, because nobody handed me that. I just have been handed P. So let's not worry about P inverse. If we multiply everything on the left by P, then you get to this nice, beautiful equation right here. And what we can do is start with A times P and hopefully find out a relationship between the entries or the rows or the columns of A times P and P times D. Well, let's see. A times P. Well, as we know, when you multiply two matrices, the product is going to be a matrix where the columns of that brand new matrix are going to be the matrix on the left times each column vector of the matrix on the right. So the first column of A times P is A times the first column of P. The second column of A times P is, well, the matrix A times the second column of P, and so on and so forth down the line. That's what we get right here. Now we're saying that's supposed to equal P times D. P times D requires a little extra work here. Remember, P is a matrix where the columns are going to be listed as P1 all the way to Pn. And D is a diagonal matrix, in fact, this diagonal matrix right here. And the way we're going to talk about this product, I want you to really focus in on the fact that I'm going to be talking about rows times columns. For example, in the product PD, let's focus just on the first row, first column entry. So you will take the first row of this matrix P here, which is P11, P12, P13, P14, all the way to P1n, and you're going to multiply it by the first column of D, which turns off everything except for the first entry. So that first row, first column element in P times D is just going to be D11 times the first row, first column entry in P. Now, if you go to the second row, but first column, again, it'll take the second row of this matrix here. It'll multiply each entry in that second row by the first column of D, which turns off everything except for the first entry in that second row of P. And this process continues forward until you get all the way down to D11, Pn1. And then you would move to the first row, second column, and you could see the second column is actually just going to turn off all the entries in every single row except for the second entry, and so you get something that looks like this. Now, if you take a look at that product there, this is just D11 times the first column of P, this is D22 times the second column of P, and so on and so forth down the line. That is a justification for this notation that you see down here. So again, the matrix A times P is going to be this. These are the columns of that matrix. But remember, A times P is P times D, and that is actually going to be equal to these column vectors right here. So therefore, each of those column vectors, AP1, AP2, all the way to APN, should equal these column vectors, D11P1 all the way to DNNPN. Therefore, if you just look at the ith column, that will imply that the matrix A times the vector P sub I should equal D11, or DII, sorry, times the matrix P sub I. But that should look hauntingly familiar. That's telling you that P sub I is an eigenvector and D sub II is its associated eigenvalue. And so the diagonal entries of D, which are these guys right here, are the eigenvalues of A with corresponding eigenvectors as the respective columns of P. Because again, these P sub i's came from P. Specifically, if we let lambda sub I equal D sub II in our notation, then we get the following. A is equal to, maybe I should have described this a little bit better, A is equal to P D P inverse. Again, that's from above. Well, I didn't really write it out, but if you were to multiply on both sides by P inverse, this guy right here, then you'd get A is equal to P D P inverse. So if that's the case, we can say, well, I know what P is. P is this matrix of column vectors P1 through Pn. I now know what D is. D is the matrix, the diagonal matrix, where the entries are the associated eigenvalues for those eigenvectors P1 through Pn. And then P inverse, I don't need to find it here. Thus, if A is diagonalizable, the matrix P consists of the eigenvectors of A, and the diagonal matrix D consists of the respective eigenvalues along the diagonal. Since P is invertible, the eigenvectors must be linearly independent by the invertible matrix theorem. Remember, P is the matrix of eigenvectors, but at the same time, because A is diagonalizable, P has to be invertible. So all those eigenvectors have to be linearly independent. If they're not, then P is not invertible. So we now know we have a bunch of linearly independent eigenvectors. How many? Well, this is an n by n matrix, so we have n linearly independent eigenvectors for this matrix A if it's diagonalizable. And that's what I write down as the punchline basically. A is diagonalizable will imply that A has n linearly independent eigenvectors, these vectors forming the columns of P and the associated eigenvalues forming the respective diagonal entries in D. This is a lot to listen to, it's a lot for me to say out loud, but it is very important that you understand that. So when you go to diagonalize a matrix, if somebody tells you, oh, I've got a matrix, it's diagonalizable, you know all I need to find are the eigenvalues, eigenvectors, then I have that magical matrix P that is invertible that will cause the similarity transformation, or actually really define the similarity transformation so that I can get my diagonal matrix D, but there's no need for me to compute that because I know the diagonal matrix D is just a matrix full of eigenvalues. Now we're going to try something a little bit different, not too terribly different in fact. We're going to go the opposite direction. So remember, we had just arrived at the fact that if we have a diagonalizable matrix A, then A must have n linearly independent eigenvectors. And then there was this subsequent little statement that, by the way, those eigenvectors will create P and the eigenvalues will create D, the diagonal matrix. But let's suppose instead that we have a matrix A and it has n linearly independent eigenvectors. And let's also suppose that we know the associated eigenvalues. So again, suppose we have a square matrix, it has n linearly independent eigenvectors, P1 through Pn, with associated eigenvalues, lambda 1 through lambda n. Well, what could be the result of that? Well, nothing as written until I say, well, let's form a matrix from those eigenvectors. And you nod your head and say, okay, I'm with you 100%. And I say, well, then A times that matrix. Let's take a look at that. Well, A times that matrix is just A times P sub 1 all the way to A times P sub n. That's the matrix of column vectors there. But we happen to know something very special about those vectors. They are eigenvectors for the matrix A. That is, when you multiply A times this eigenvector P sub 1, it should end up being lambda 1 times P sub 1. And when you multiply the matrix A times this eigenvector P sub n, it should be lambda n times P sub n. And that's what we're going to say right here. These matrix products are all equal, but using the same exact logic that we used in the previous page, we could say that product right there, that matrix, this guy right here, is the same thing as this stuff right here. You can double check, but this is actually what we did, the opposite of what we did, but what we did in the last page. And by the way, that is the matrix P, and that is a new matrix we'll call D, where the diagonal elements are the corresponding eigenvalues. You can see that we're almost to a punchline. I have it right down below. Since the columns of P are linearly independent, P is invertible, and so P inverse AP must equal D. Again, you might look at that and go, wait, how did you get from all that argument to there? I was with you up to this point, but how'd you get to that point? Well, we already have shown AP is equal to PD right in the statement above this ink. So if P is invertible, just multiply both sides of this on the left by P inverse, and you will get to that statement right there, which tells us that there is a similarity transformation that takes A and maps it to a diagonal matrix D, specifically the diagonal matrix D full of eigenvalues for A. That's what I say right there. Thus, A is diagonalizable. The punchline to this statement is A has n linearly independent eigenvectors. Well, that will imply A is diagonalizable. But remember, on the previous page, I said we proved that if A is diagonalizable, then A has n linearly independent eigenvectors. We have proved a massive theorem in linear algebra. It's called the Diagonalization Theorem. And there are a lot of pieces to it, but actually most of them we already know. So an n by n matrix A is diagonalizable if and only if, well, by definition, is diagonalizable if and only if there's some invertible matrix P such that P inverse AP is equal to D. That's just from definition of being diagonalizable. So this statement here and this statement here, they fall out from each other. That's just from the definition. And by the way, since P is invertible, this equation right here is true if and only if this equation right here is true. So again, all that falls out from the definition, nothing more. However, what we've just proven is that last statement at the bottom, which is that A has n linearly independent eigenvectors. That's really what we would call the diagonalization theorem. But there's a little bit more to that actually. That's true if and only if the columns of P, part of that similarity transformation, are n linearly independent eigenvectors of A. So if you start with some matrix that contains n linearly independent eigenvectors of A, you know immediately A is diagonalizable, as long as A is an n by n matrix. Frankly, I ran out of colors to highlight with, so you get the same highlighter as the first one. That last sentence, in this last case, the diagonal entries of D are the eigenvalues of A that correspond respectively to the eigenvectors in P. That is, if lambda sub 1 is in the first column of D, then its associated eigenvector must be the first column of P. And if you have an eigenvalue that's in the 10th column of D, then its associated eigenvector must be in the 10th column of P. So now we know if somebody walks in the room and says, hey, I got a diagonalizable matrix, there's a lot of stuff they've handed you. They didn't hand you, by the way, anything about A being invertible. That is not part of this theorem at all. But they did hand you the fact that A does have n linearly independent eigenvectors, and they told you how to form the columns of P for the similarity transformation and how to form the diagonal D, or the similar diagonal matrix to A. Now, a bit of a warning about this theorem is really only true over the real numbers. So if you're dealing with complex numbers, then not that all bets are off, but you have some extra little work to do here. And because I don't really play with that in linear algebra, we do in differential equations, but in linear algebra, we'll just work over the real numbers. Now, originally this video was actually going to go a lot longer, but I decided as I was editing to go ahead and cut it right here. So let's go ahead and take a break, and we'll come back in the next video and finish out a conversation about diagonalization. I hope to see you there. Have a great day. Be a wonderful human.
It's the system of equations must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry. Don't